So we've got one last example in this section. We're going to talk about testing a power series for convergence and then how we can determine that radius of convergence. So the first thing we're going to do is we're going to use our ratio test, or we can use the root test to find R. And R is going to represent a radius of convergence. And the way we define that R value, we say x minus a is going to be less than R. Or rather, negative R is less than x minus a is less than R. Or a minus R is less than x is less than a plus R. So we're basically thinking about this R, how far off can we be to the left or right of that specific a value in our power series polynomial. So we know two things about R. So as long as R is a finite value, we're also going to need to make sure we test at those endpoints for convergence or divergence. And some tests we might like to always use would be the comparison, the integral, or the alternating series test. And if we determine divergence, so if R is finite and we know that it diverges, then we are going to use that x minus a, and that's going to need to be greater than R. Okay? So let's talk about a theorem now. So if the sum from n equals 0 to infinity of a sub n x to the n, if we know it converges absolutely, so if we know it converges absolutely for any x that is less than that R, my radius of convergent, and if we know f is continuous, then what we can say is that sum, n equals 0 to infinity, of a sub n, treating that as a function, f of x to the n power, converges absolutely. And it converges absolutely on the set of points, or the interval, of x, where the absolute value of f of x is less than that radius of convergence. So let's do one example. So let's find the series interval of convergence. And within this interval, we're going to determine the sum of the series as a function of x. So here we have the series 0 to infinity, 3 to the nth power times x to the nth power. So we'll start this problem by looking at what our terms are and trying to get a gauge for what this series does. So if I start listing out my terms, I end up with 1 plus 3x plus 9x squared plus 27x cubed plus 81x to the 4th, going on and on. And what we notice is that this is geometric. We have a first term, and we know that our common ratio, R, is 3x. And the ratio can be found by taking a term and dividing it by the term that comes before it. So the first thing we'll do is we will use our ratio test again here. And before I do my limit to infinity, I'm just going to set this up. So my n plus 1 term would be 3 to the n plus 1 times x to the n plus 1 over my nth term, 3 to the n x to the n. And this would simplify using division, subtracting exponents. I get the absolute value of 3x. So that is my ratio. I can rewrite that as 3 times the absolute value of x. And what we want to do with our ratio is we want to determine the limit as n goes to infinity of 3 times the absolute value of x. Now this limit is dealing with n, not x, so I can pull the x out in front of the limit. I've got the absolute value of x times the limit as n goes to infinity of 3. And that limit, because it's constant, that limit goes to 3. Okay, so we end up with 3x is equal to my rho value. And by the ratio test, if we want to find convergence, we need rho to be less than 1. So I take this and I say 3, absolute value of x needs to be less than 1. Divide by 3 on both sides. Absolute value of x needs to be less than 1/3. And that gives me negative 1/3 is less than x is less than 1/3. So this is my interval. This is my radius of convergence. But we need to test each endpoint. That's going to be important here. And we've seen that in the previous examples as well. So what happens at x equals negative 1/3? So that would give us the sum, if we did x equals negative 1/3, sum from n equals 0 to infinity of 3 to the n, and that would be negative 1/3 to the n. And that sum would then be the same as writing 3 times negative 1/3 to the n, which is just going to be the sum n equals 0 to infinity of negative 1 to the n. So this is a divergent alternating series. That's what we have there. And we'll also test the other endpoint, positive 1/3. So at x equals positive 1/3, what does that sum look like? We have n is 0 to infinity of 3 to the n times positive 1/3 n, which gives me the sum as n equals 0 to infinity of 1 to the n, which is the sum as n goes from 0 to infinity of 1. And if you sum 1 infinite times, it's going to become infinitely larger. So this is a divergent, infinite sum of a non-zero constant. All right, and we know this is divergent. Okay, so where is the series convergent? The series is convergent, or it converges, when x is between, on the open interval, from negative 1/3 to positive 1/3, but not at the endpoints. And since this was a geometric sum, the sum of my series is going to be that first term, which is 1, divided by 1 minus the common ratio. We had 3x. So this represents the sum of my series and my radius of convergence, the interval over where it is convergent. And let me just fix that spelling error right there before we pause it. All right, all done here.